Okay, let's continue on. So some specific examples we're going to do in lecture. I want to continue on with kind of the more abstract notion of probability and some techniques, some rules that will allow us to make practical calculations that will be necessary. And so we kind of want to set up the machinery to do this. Now, this is not a class on probability. It's not a mathematics class, and it's not a mathematical logic class. Nevertheless, we need to use some of these concepts. And so what we'll have to do in certain cases is, depending on how far we need to depart, we either accept certain things as true, and I point you to be able to look them up. Most of the time we will try to expound kind of upon most of the details. And sometimes I will be quoting rules that one can convince oneself of, generally speaking, by doing a couple of simple examples, but that we will not go on to prove rigorously in a way that they might be in a mathematics class. And so I just want you to realize that that's what this is going to look like. If, for example, you were interested in the proof of a specific theorem or rule that we're going to liberally use in this class, I can certainly point you to certain resources that would allow you to understand it. Now, I will say that the book by Bayerlein, the last book that I recommend in the syllabus, goes through some of these derivations. It also stops short and does not act like a mathematics textbook because that's not what it set out to do, but that's just something you need to understand. And so with that preamble, here we go. So I want to come back for now, not to the coin toss example, but to the example of tossing a die. So we imagine we have an ideal die that contains 6 faces that we're going to attempt to draw. So perhaps this die is going to look something like this. Oops. And then perhaps this is face 1, this is face 2, this is face 3, and so on. And so a die is tossed, and the possible outcomes are outcomes, or let's say possible outcomes. Let's actually put in that this is a 6-sided die. The possible outcomes or inferences about what's going to take place after a die is tossed. Again, assuming the die is perfect. None of the faces are any better than any others, and there's nothing that is intrinsically preferred by nature or the die toss or the die itself that prefers one face over the other. That is to say, this is an unbiased die, where you expect that at any given point, any one of the faces could show up. The total number of possibilities, or the possible outcomes or inferences, are 6 in number. If we list them, they are, of course, 1, 2, 3, 4, 5, 6. And our degree of rational belief in obtaining any one of the faces when a die is cast, when a die is thrown, given that this is a perfect 6-sided die, we believe that the probability of any one face showing in a single die toss is 1/6. That is to say, any one face, let's say the face 4, it again is not preferred over any other face. There's a total of 6 possible outcomes when we die is cast. 4 is only one of those outcomes. So we expect that out of every 6 throws, a 4 will be found once. Once again, we imagine that this is die is cast or thrown many, many, many times. And the total number of, let's say, obtaining 4, total number of times the 4 was recorded is written down, recorded, and divided by the total number of die tosses. Now let's think of a slightly more complicated question in a sense, asking for a slightly more complicated inference. What is the probability that you obtain either a 2 or a 4? What's the probability that a 2 or a 4 is found? So this brings us to rule number 1. And before we talk about rule number 1, we have to first make a couple of definitions. When we throw a die and we record the outcome, We know by the design of our problem that any one of these faces is going to show up. But only one of the faces is going to show up. You're either going to find a 1 or a 2 or 3 or 4 or 5 or a 6. That's the only possibilities. What we say is that the possibility of obtaining a 1, possibility of obtaining a 2, possibility of obtaining a 3 or 4 or 5 or a 6 are mutually exclusive. When one is obtained, the other ones definitely did not obtain. There's no possibility of observing both a 1 and a 3 in a single die toss that lands with a single face showing up. We don't admit crazy possibilities of a die accidentally landing on a corner showing 2 faces. Or like the die being tossed on the ground, coming to rest on the side of a carpet that begins and props it up at 45 degrees. We imagine a much more ideal circumstance. And so the outcomes are mutually exclusive. Mutually exclusive. Here's the rule. The probability that a 4 or a 2 is obtained. So what does that mean? What are the possibilities? Probability 2 or 4 are obtained. This is not going to be 1/6. And the reason why it's not going to be 1/6 is that we expect intuitively that this probability is going to be larger. Because if we were only looking for a 2, we expect that to occur 1 out of every 6 times, with a probability of 1/6. But sometimes now 4 will be obtained in those however many outcomes. And so the probability that this or that is obtained is expected to be larger. And the rule is this: if the outcomes are mutually exclusive, the probability of obtaining a 2 or a 4, and this or operator is a logical operator. In the logic of probability, this is known as a disjunction. If a 2 or a 4 are obtained, that we're going to be satisfied with either one of the outcomes. That's our inference, that a 2 or a 4 is obtained. The rule is this: probability that a 2 is obtained plus the probability that a 4 is obtained. It's the sum of the two. And this is going to be 1/6 plus 1/6, which equals 1/3. So a third of the time, a 2 or a 4 will be found. That's the rule. When you are interested in obtaining the probability where more than one mutually exclusive outcome satisfies your inference, a 2 or a 4, not and, not together, but any one of them might appear, and we are interested in one or the other, the total probability of that inference is the sum of the individual probabilities, of the sum of the probabilities for each individual inference separately. Here the two inferences are combined into a single kind of master inference in this sense. Master outcome. Or master combination of possible outcomes, where you're okay with either one. And this relies critically on the idea of mutually exclusive outcomes. Now, if the outcomes were not mutually exclusive, and you can maybe think of some cases where you don't necessarily have mutually exclusive outcomes, there is a formula that exists that can be derived that allows you to still calculate that probability. But for us, the form is particularly simple. Everything that we'll be dealing with will always have to do with mutually exclusive outcomes. And so when we're asked for the probability of either inference, we add the probabilities. What about the probability that a 2, a 4, or a 6 is obtained? Well, we've now added a new inference. Instead of a 2 and a 4, we also have the possibility of a 6. So another term, 1/6, would be added, giving you a probability of 1/2. That is to say, you've essentially colored 3 of the 6 faces the color my outcome. Maybe that color is red. And so if 3 faces were painted red and 3 were not, you expect to half the time get the painted faces. The painted faces in this case, in this example, would be the 2, the 4, and the 6. Let me modify this further still and ask kind of a ridiculous question, but this will point us to a critically important rule or expectation that you all are aware of. What about the following inference? Oh, this whiteboard is kind of crappy. Or maybe it's the eraser or the marker kind of crappy. We'll see. What about the following inference? What about the inference that when I throw a die a single time, I either get a 1 or a 2 or a 3 or a 5 or a 6? Probability that 1 or 2 or 3, yeah, I'm going to keep doing this, or 4 or 5 or 6 is obtained. Obtained. This equals, according to our rule, given that all of these are mutually exclusive outcomes, 1/6 is the probability of obtaining a 1. 1/6 is the probability of obtaining a 2. 1/6 is the probability of obtaining a 3. 1/6 is the probability of obtaining a 4. 1/6 is the probability of obtaining a 5. And 1/6 is the probability of obtaining the face 6. We add them all up. We have 6 times 1/6. And the answer is 1. When we sum all the mutually exclusive outcomes, or said another way, when the inference that we are asking the probability of is what is the probability of obtaining any one of the possible mutually exclusive outcomes, and if our inference is exhaustive in the sense that it asks for any one of the possible outcomes, it exhausts the sample space, the total probability is 1. And because we know that when we throw a die once, one of the faces definitely obtains, we can't know for a fact before we actually throw the die which face will obtain. But we know that no face is preferred, and 1 or 2 or 3 or 4 or 5 or 6 will definitely obtain. One of them will definitely obtain. And so when you ask for the probability that any one of these outcomes is obtained, that you're satisfied by any one of the mutually exclusive outcomes, well then your inference is going to be certainly correct. Any one of the mutually exclusive exhaustive outcomes will definitely obtain, and we get the number 1. One thing we didn't really discuss or spend time on, but we can talk about now, is that when we speak of probability, the numerical value 0 represents no chance whatsoever. When we say that obtaining a certain outcome has a probability of 0, we mean that no matter how many trials you do, you will never find that outcome to be the case, to be true. And when we say that a certain outcome has a probability of 1, what we mean by that is that the outcome is certain to be the case. It is definitely going to happen. There's no uncertainty. It is absolutely guaranteed to happen. The numerical value 1, and in fact the numerical value 0, are choices that we've made, and we've agreed on this choice without really saying it explicitly. We all believe, and we're all in agreement, that certainty is represented by the numerical value of probability being 1. In this case, certainty is associated with any one of the outcomes being true if the number of outcomes that your inference contains is mutually exclusive set of exhaustive possibilities. And so, in a more abstract way, let us go back. Magic. Whoops. Move back. In a more abstract way, if you have a set of inferences, let's say you have a set of inferences that you can number 1, 2, 3, all the way to n, we say that the sum of the probabilities for each inference labeled with the I, where I is an integer in this case that goes from 1 to n, if this set, if the n is an exhaustive set, exhaustive set of mutually exclusive outcomes, this quantity is equal to 1. And we refer to this property as the normalization condition. That is familiar to you, at least from quantum mechanics. And this effectively follows from the rule that we've already discussed that is more general than this, but ultimately we arrive at certainty being associated with the sum of the probabilities for all the possible outcomes. Now let's discuss another case that we'll use again. So the previous example that we looked at, let's actually go back again. Let's do some more erasing. Now, suppose we modify the problem a little bit. Instead of tossing a die once, we're going to toss a die twice. Or alternatively, we have two identical dice that we toss at the same time. But the bottom line is that there's going to be two sequential or simultaneous events where two outcomes are recorded. The face of the first die and the face of the second die are recorded. And suppose we want to ask for the following question. What is the probability that the first die gives a 1 and the second die gives the face 4? Critical point in that is and, not or, not either outcome, but and, a simultaneous demand. And so toss two identical dice, identical 6-sided dice, and ask for the following probability. Again, the number of outcomes for each individual die is 1, 2, 3, 4, 5, 6, and they're identical, so that's true for both of them. What is the probability that you get the face 1 in the first one, the face 4 in the second one? So let's write this in our notation. Let me erase this now. The probability that 1 for die, let's say A, actually let's not, well, okay, fine. Two identical 6-sided dice, A and B, labeled A and B. I don't mean to confuse you, but this is not the outcome general A that we used before. These are just the labels that we're going to put on the dice. So we obtain the face 1 for die A and for die B. What is the probability that both of these events take place? That we're not going to be satisfied. Our inference is not obtain die A with 1, but something else for die B. We want die A to give us the face 1 and for die B to give us the face 4. When die A gives us the face 1 and die B gives us the face 3, that is not the inference that we're asking about. We're asking about this specific conjunction of this inference and that inference together, and, not or. Here's the next rule. First, we realize the following. Does the fact that die A gives us 1, does that fact have any influence on whether die B gives us 4? If the dice are identical and ideal and we toss them simultaneously, why would die B have anything to do with what die A does, or vice versa? Or even if the dice are tossed sequentially. The fact that die A, the first die, gave us face 1, and die B gave us face 4, we intuitively believe are unconnected. There's no reason to expect that the fact that die A gave you a 1 is going to somehow induce die B to give you a 4 or not give you a 4. And so we believe that those events are independent. The probabilities for them are independent. They are uncorrelated. The fact that you get 1 does not have anything to do with the fact that you'll get the other. The rule in this case, if you're asking for a joint outcome, a joint probability, let's call this joint probability. Joint probability from the perspective that it joins two events. It joins the outcome of die 1 with the outcome of die B. So this joint probability that is composed of an AND logical operator. The rule is that if the probabilities are independent, uncorrelated, the probability for the conjunction, for the joint operation, for the two events simultaneously, or in the same trial of two die throws. Now a single trial is being thought of as two die throws. The probability is a product of the probability that 1 is obtained for die A times the probability that 4 is obtained for die B. It's a product. And we know the probability here for any face is 1/6 and any face is 1/6. So this is 1/6 times 1/6 is 1/36. Notice that before when we were asking about the probability of or this or that, we were satisfied by two mutually exclusive outcomes as our composite inference. The net probability of this or that was larger than the individual probability because now we could be satisfied by two outcomes. The likelihood that either one of our outcomes together, if we don't care about two specific outcomes, for example, was greater than any one of them. Notice here that the final probability is smaller. That is to say, you are less likely to obtain this face and that face together as opposed to any one of them, because now two things have to come to fruition. Each one of them has already a reasonably low probability, but two things coming together at the same time, this composite inference, this and that, is going to be even less likely. There's another way you could have found out what the probability for this was, and that is to write out the sample space And the convenient way to write out a sample space for 2 die throws is to make kind of a matrix, a table, where you label 1, 2, 3, 4, 5, 6 as the outcomes of one die. You label the row, I'm sorry, the columns of the outcome of the other die. Stay with me now. So each one of these boxes is a possible outcome of a 2 die throw. We are interested in the outcome where we get one face on die A. Let's say this is die A. Let's say these are the outcomes for die B. And so a 1 on die A and a 4 on die B. So this is the specific inference, a specific event, the composite event that we're looking for. And so how many outcomes of the total number of outcomes? First of all, how many total number of outcomes? How many boxes? Well, 6 in one direction and 6 in the other direction. 36 total outcomes of combinations of one face on one die and the other face on the other die. How many among these 36 is the inference or the outcome die A with 1, die B with 4? Just 1. And so the probability is the total number of outcomes favorable to our inference, or where our inference is true, divided by the total number of all possible outcomes. There's only one outcome that satisfies our inference. There's 36 total, so the total probability is 1 divided by 36. Or, as we found, we could find, because the probabilities were independent, as the probability of the first die times the probability of the second die, a product of the two. But you could have found it either way. And of course you can imagine more complicated combinations of 3 dice, 4 dice, and then you run out of dimensions quickly. But certainly you can store that information on a computer if you wanted to. And so these are the 2 main rules with which we're now familiar. One of them, the first one, has to do with the question or. When more than one outcome satisfies your inference, in that case we add the probabilities for the individual inferences if the probabilities are mutually exclusive. If the probabilities are mutually exclusive and they're exhaustive, and we add them all up, that is to say, any one of the possible inferences, we always get a 1. Meaning that one of the inferences is going to be true, definitely. They're exhaustive. And if they're mutually exclusive, then they sum to 1. Now, in this example, how would we modify this? Or how would we use both of these examples? Well, we might ask for the probability that we get either a 1 and a 4 or a 3 and a 6. So if we ask for the probability that we obtain 1 for A and 4 for B, or what did I say? Whatever. 3 for A and 6 for B. So first, both of our inferences that are squeezed between this or are themselves composite inferences. They represent joint probabilities. But the or says more than one joint probability, more than one joint inference will satisfy our what we're asking about. And so we are either looking for a 1 on A and a 4 on B, or a 3 on A or a 6 on B. That's our inference. What's the probability of our inference, where our inference is satisfied by both of these outcomes? Well, we have the 1 and 4 already selected. Here's the 3 and 6. We have two possible inferences that satisfy our, two possible outcomes that satisfy our one composite inference. So the total probability should be 2 over 36. How else might we find this? Well, we know that the probability for this, we figured it out already, is 1 over 36. We know that the probability for this is 1 over 36. So the total should be 1 over 36 plus 1 over 36, which is 2 over 36, which is consistent with what we just did there. So those are the rules of probability that we're going to be using extensively. I hope that you stop and pause and think about what this means. We'll do more examples of this with coin tosses, just like we did in the lecture notes in our Zoom meeting. But that's what I wanted to say.